So guys, I wanted to show you this to start with. This is actually, so a lot of websites, there's an enormous amount of work that goes behind them. It's just, you know, unless you do it yourself, you don't appreciate it. So this is something, because we've built other websites, we know the pain behind it. It's a company we're connected to, organization we're connected to, Mata, that's been building, taking this work that we've been doing on measuring happiness, which, this is from Twitter, but really from any kind of source. So this is ending in 2013, starting back in 2009. There's going to be some corrections to this. The different colors, so this is an online interactive thing, right? The idea is we'll have this up running. You'll be able to stream things off it. We're trying to put this up against, say, GDP and so on. And there's a lot of refinement to go, but it's not too bad. There's some nice things about this so you can, do this. It's a little fancier. It's better than the PDFs we make over and over again. So the colors, which there's a little legend up the top, but red is Saturday, and light blue here is Tuesday. Tuesday's on average the lowest day of the week. Right? So Monday's pretty bad, Tuesday's a little lower, and then there's a slow climb up. Friday's pretty good, Saturday's great, Sunday's a little down, and then Monday. But the worst one's Tuesday, because like the weekend's gone and it's a long way away. So it's not Monday, it's not the Monday. So there are lots of interesting things that pop up in here, and we've improved this instrument, which we call a hedonometer, to we've refined it. It's very much like it's behaved so far like a physical instrument. Like you polish the lens and you get a better image, right? And it doesn't change the image so much that you're looking at a frog becomes a banana or anything. Well, that was all the things I said before were wrong. We're increasing the resolution, so you still see the same pattern, but we see some more detail. And one of the things that essentially we've been getting more words involved in our analysis. You actually see a lot of these negative things pop up. So this is a tsunami, for example. We couldn't see this before. Very sadly, this is Sandy Hook. This was always there. You can see that's Michael Jackson. These little pop-ups kind of give you an idea of which words are contributing. So the big days, the big positive days are things like Christmas, right? So it's Christmas. Valentine's, that's Easter actually. Valentine's does well. You can see the words. Again, that's Christmas. Overall, and I can't really show you the whole thing. Overall, you can see there's a bit of a downward trend there. So good. And then, of course, the demographics have changed over time, so it's more complicated. This is just Twitter. We want to put a lot of different streams, whatever, BBC, and we have some of those. It's a good testing ground. And then you can add in all sorts of other things. Like you just want tweets from California, or you just want tweets that are in Spanish. We're getting many other, on the order of about 10 to 12 other languages scored, and then we'll move to phrases actually. So it's going to be much more complicated, I think.
Sorry, what's the vertical scale?
So the vertical scale, I'm not going to. So it's a score we've come up with for happiness. It's pretty simple in a lot of ways, but basically, we take a text that has to be sufficiently large, break it down into its constituent words, and we have individual scores for the words. So it's going to get things wrong, but it's very much like measuring the temperature. Right? Some molecules going this way or that way and so on, and they're not as excited as the others, but we're getting a very much on average thing. It's certainly improvable. Actually, that's the bailout down there, so that's the start of it. This data starts back in 2008, and this is when we started to get data from them, and they only had 4 people working for them, right? And of course, they called it Twitter, so they didn't think it was going to become anything important. Now we embarrassingly have people tweeting, saying that they tweeted. So you see, the ones that are positive, the ones that really stand off as positive days are all predictable, in a sense that they're just annual events. People say nice things. So it's not just saying Happy Thanksgiving. People are talking about family and friends and food. And there's less of not and don't. So there are these little pieces in there that add up, that tell you it's not just about that. If you look at Saturdays, for example, which in general, as you can see, these red ones are happy. Yes, there's a lot of things like party and Saturday. These are all good words, right? Ends are in there and so on. There's also drunk and hangover. So there are some molecules going the other way. And bored, right? Bored is there as well. So, but generally speaking, it's a good day. usually people start to tell me how they feel about particular days, and it's usually just explaining what their family is like. So, so you should resist that in any of these things. It's very tempting. So, yes?
I know that there are some peaks around roughly at the end of the year or beginning. So
Yeah, there's a bit of a, it seems to be a bit of a struggle. We notice this in blogs as well, right? So you have, so that's Christmas Eve, this Christmas Day is here, then there'll be New Year's Day here, so that's all good. But you see this drunk and hangover, these are considered to be negative words. There's a little less negativity, less no, not, don't, so people are saying those things relatively less as compared to the weeks around it. Of course, they're saying Merry Christmas less because it's been compared to the week before, but there's more drunk and more hangover. But the balance is positive kind of thing. And then, yeah, January is always a bit of a struggle. People don't know what to do with it. You know, you've had your big celebration, and then winter takes, you know, it's another 5 or 6 weeks before it starts to warm up or something. You know, it's just, what are we doing? You know, you have to go back to school. It's just not a great time. So that seems to be generally true, right? There's a nice dip there. That's another one. That's another one, right? And we're into this one here.
it's not on March also. It seems like something happening on March.
So here, well, okay, so there's some work to be done. This is still a experimental thing. This isn't live online yet. There's some patching to be done, I think. Yeah, there's probably a break around here somewhere where there are two different data sets being merged. But things kind of climbed up again here, so we've dug ourselves out a little bit, but sort of on a bit of a decline overall. But again, it could be changing demographics. So it's just one thing. So anyway, it's exciting. These little popovers, which will be improved, are kind of a big deal for us. So, sorry, to be amused by that. So today, so I want to mention that just for fun. We do lots of different things. That's one of them. I want to talk more about robustness. I'll give you a little piece on language, just some interesting stuff about language and scaling. It's the evolution of language story. Just a little piece there, very interesting bit of work from a few years ago. I might add to that I want to add to that as I go on. There's a whole huge lecture on language that I could put in here. And then I want to talk about bad behavior, where power laws aren't power laws, they're dressed up as something else, right? So it's going to be lognormals. And other beasts that have these heavy tails, these fat tails, as it were, and reasons for why they might come about, right? So there's this sort of bestiary of horrible distributions, right? These distributions of surprise where bad things can happen. You're going along sampling away from this distribution and everything is small, and then kaboom, and it's a big surprise. Never happens for a Gaussian. But these ones with these heavy tails have many, many stories for why they come into existence. I've tried to give you the big ones, the rich gets richer story being, I think, the most dominant one. But I'll show you how if you tweak those stories a little bit, you end up with other kinds of distributions. And then people argue like crazy about these things, but it's just good to know. So you certainly don't want to walk out and say, hey, that's a power law and it's a rich gets richer scheme. Fine, I understand it. It's not true. Okay. You have to get into the details to support those stories. All right. So we saw this. I'm going to try to code this up for you guys so you can play around with it in a coming problem set. But this story was a design kind of problem. This is a bad forest, which was built with a random design approach. This is the very good forest, which was built in a sense with full knowledge, kind of, but it's iterative. And as we talked about the other day, so it's in response to an uneven, uncertain environment. In this case, it's lightning strikes or pyromaniacs, more disproportionately located over here. There's sort of an unevenness in the X and Y directions. And the fire breaks, if you like, have been built in response to them. So just to reprise that, so I'm going to talk very briefly about how we could approach this theoretically. This is really demonstrations. So it's robust yet fragile. And the big deal was that the big departure, and I want to iterate this again, I'm going to talk about self-organized criticality, is that there's no critical point for the system. The system doesn't have to be at some special critical point. You can have densities of trees This is a percolating critical point here where there's a sort of tree, little subforests of all sizes. Yeah, there's an enormous forest in here, right? They're really connected. And but you're still getting a parallel distribution of sizes, even though you're well above what we call the percolation threshold. So, and there's real structure in there, right? So it's a very potent story. And I'll point to a paper that appeared in PNAS from these authors, Carlson and Doyle, that you should read. It's a general kind of thing. Okay, so here it is. It's complexity and robustness. Carlson and Doyle, so it's 2002. It's a very general piece, and I'll make this comparison in particular with their model and what's called self-organized criticality, which I'll introduce you to in a little bit. They have a slightly more complicated model than I'll talk about here, but you can see that this is a log scale. There are lots of different things here, right? So this is data coding over here, this is forest fires, this is to do with the web, so lots of different things. This is actually not really parallel. But so parallels are straight lines, right? These size distributions with decaying parallels will be straight lines. You can see there's some curvature here, right? And so they're getting out that kind of extra structure, which again is sort of, well, similar in some ways to Simon. Simon managed to get the ends of the model quite well, although it was a pure parallel that he was talking about. Here they're fitting things quite spectacular. So that's an extra piece, just to show you the potency of the whole thing. So where we want to start today is with the so-called hut theory. So let's think about how we might explain these kinds of distributions. It's very abstract. It's just a little piece. And you'll be able to finish some of it in your problem set, next problem set. So we have two elements in this. We have, what we're worried about is the sizes of forests that could go up, right? So think about forest size again. But we'll talk about failure size, Y sub I, and it's correlated with some kind of resource size. So we'll see how this plays out. You'll see that it's very much a dimensional kind of story. So if you think about forests, there's a border around it, right? If we've done a good job, there's a fire break around it, right? So there's a one-dimensional structure around a two-dimensional structure in that case. If we think about data coding, we'll have one-dimensional pieces with zero-dimensional breaks inside. You could imagine going up to three-dimensional pieces, so you imagine you have some structure that if something goes bad in here, it spreads all the way through this volume, then the envelope that's protecting that spread from going to other parts of the Death Star is two-dimensional. Right. So we want to design a system to minimize this average failure size. And there's going to be some constraint on the resources. So it's pretty simple. We're going to minimize the cost. We'll let our cost piece down. So we probably have event of size Y times the size of that event, and we look across all sites in the system. And so there's some constraint. So we're back to Lagrange multipliers, which we've played with a little bit already. Okay, so there's something about these sites. We add up everything. We could do this for a discrete story, which I'm trying to show here, or we could do it with a continuous one, just for fun. So there's something about this constraint. So there's going to be a little bit of sneakiness. Okay, so let's think of use the forest fire analogy to motivate setting up this problem. So the cost of a fire, on average, is the expected cost of a fire. So we're going to sum across all the sites. Think of this n by n lattice again. There are two pieces here. One is so this is a bit odd, right? So we have to do this now. So we've got some grid, and imagine this is a connected bit of forest, and this is another connected and so on. But we've imposed a grid on top. So here's site I, but this whole thing here is area I. It's also, if this is site I plus 1, this is also equal to I plus 1. So whichever, there's one big area they all belong to. So it's a non-local story. You're saying, okay, I'm in this site. What is the area of connected forest that I'm sitting inside? This is sometimes a bit of a tricky thing to play around with analytically. percolation models do the same thing. So I'm in this site. What is the size of the forest that I'm part of? So that's A sub I. So that's how bad it would be. So this is the probability that you get that fire. P sub I, it's probably that hits at that space. It's normalized by the area as well, so it's a bit of a funny thing. So we'll write it out as this piece. Okay. It's the area of the ice sites region, and this is probably that you get a fire. It's the average probably you get a fire in the ice sites region. Could be like it. Okay. All right, so we put those together. So this is our average cost of the fire. It's going to be probably divided times A squared. Now we have to think about what does it cost to build these firewalls. So we're going to sum across all these sites again because this discreteness helps us. We'll sum over all of these sites, and this, what we're presuming here is that this boundary, the boundary is going to be proportional to a I to the half. So it's just dimensional analysis. And it's also saying that these shapes are growing isometrically. We'll come to allometry later on. You know, growing in funny ways, right? So bigger areas are going to be roughly growing in proportional to the area. The boundary is going to be growing proportional to area to the half. So you can think of this as, well, we have to keep this clear, so there's some effort, and that's a constant kind of effort. So there's a per unit time associated with both of these. And then we divide it by area, because that is that's the cost of this boundary associated with one side. So if you add up all of these things, as you go across one whole region that's connected, then it'll total this piece here. Assuming a symmetry. So in D dimensions, this half, right? So this is area is growing like length squared, so the length is growing like a to the half. In general, if we're in 3 dimensions, then our volume would be proportional to length cubed. So a surface area will be proportional to length squared, which is proportional to volume to the 2/3. Right? So in general, it's a volume in D dimensions, it's proportional to length through D, and the surface in D dimensions is proportional to length through D minus 1. And then if you rewrite this, that's really proportional to volume of D minus 1 over D. Okay, so we can just put that in. We are talking about forest fires, but we can put that in here. There's no big change. This piece at the top will stay the same. Area would turn into volume. So there's a problem to figure out here to play with. You end up finding from these two constraints, so it's this guy plus a lambda times this guy, minimize all of that with respect to P sub I, and then we right. And then we'll end up minimize with respect to the areas. Then we end up with this distribution, right? So there's going to be this decay, parallel decay in probability of the ice site with its area. And the relationship, it'll be a gamma. We always look for these gammas. 2 plus 1 over D. So dimension appears here very nicely. So in 2 dimensions, it's going to be 5 halves. Right. So there's some work. This is just a setup. There's some work here to figure it out. Good. And it's a very rough argument, but it gives us this, it does give you the sense that parallel is going to pop out of this thing. All right, that's okay. Good. So this is just about the theory. I had a nutshell about kind of the design process. Same story, really. So we build firewalls around areas where the sparks are more likely. right? So the small connected regions are in the bad places, of course. So we see lots of little small outbreaks, and that's fine. We can handle them. We have a little ring around them to stop them from taking off. Now and then you see it, so it's robustness. Now and then you see large outbreaks, and that is idea of fragility. All right, so all of this is to be compared with self-organized criticality.
So the power law seems like as the region gets larger, already needs to be lower.
Yeah, right. So the probability of right. So it depends on the. You're given the spark probability, right? That's given. You're given the chance. You're given that distribution. Right? You're given the probability that sparks can happen, will happen in particular areas. And where it's low, then the area you tend to put around that will be larger. You need some smoothness in the distribution, obviously, that jumps up and down. That's going to be hard to deal with.
So it's by design the area of lowest need to be large.
Yes.
It's by design.
Yes. Yes. Well, you have limited, right, if you can design it, right? So if you can design it, or evolution can lead to some kind of design. It's tricky, but I'm moving right. If it can, through an evolutionary process, weed through different scenarios, and that means that the uncertainty of the environment can't change too much. If it changed dramatically, then you're in a lot of trouble, right? So if the lightning suddenly moved to the bottom corner over here, then while you had a great design for this still uncertain environment, so it's funny. It's not brittle. It's fragile, right? It's not as if. I mean, it is withstanding a somewhat uncertain environment, where it changes in the environment. It's a stochastic environment. The environment has an unpredictability to it, but it's characterizable. You can give it a distribution. So that distribution is stable. If the distribution fundamentally changes, then it's bad. So it is designed to cope with a certain level of uncertainty, but not really big changes. Right. But again, you have a limited amount of resources. So you could put little fire breaks everywhere if you wanted to, and be very clever and so on. But if you have a limited amount, then you start to really say, really cordon off the places that are in trouble. Right? You start to put a lot more lightning. The lightning chance is much higher here. Then you start to really reinforce that area. Right? So you might put in another fire break here and so on and so on. If this is a much more probable thing. And then you just give this up. Right. So it's a low probability. The way it works is through dimensionality, right? It's the area is connected to the boundary, and that's where these exponents are coming through. So self-organized criticality. Sort of a big deal for a long time. It still appears that there may be some systems that kind of achieve the idea of this story, which is, so we talked a little bit about magnets, right, the Ising model, and there's this observation that we see over and over again in these statistical mechanical systems, but there's this critical point, right, that matters. And usually the big deal is that on one side you have a phase that's got some order and structure, on the other it's randomness, and fair enough. But there's only one point, and really close to it, that's similar, but there's really only one point where you have these parallel distributions that we keep seeing in the real world over and over again. So this idea, it's by Perbach and two colleagues, it was published in 1987, I have it on the next slide, was that these parallels are arising because, in analogy to magnets and all these sorts of things, that somehow natural systems are moving themselves, that they're changing their temperature, if you like, so that they are at these critical points. So there's some self-organization, right? So we had this story of so we had the magnet story. So here's temperature, and this is the critical temperature. This is everyone is pointing up. This is everyone is pointing down. and this is overall magnetism. So as we cooled it down, we started to see either way would happen, right? We start to see all these spins starting to line up with each other. But this temperature is an external dial here, right? We're depending on where it's coming from, we're turning it up and down, right? Whether it's the sun or we're heating up a room or something, where this dial is an external parameter. Self-organized criticality says that this becomes endogenous to the system and that systems find that point. They naturally find that point. And so you have some beautiful ideas that this is order and chaos, you're on the edge of it. Sounds great, right? So somehow systems find that. The whole HUD story is that there are actually large realms of parameter space that can be found somewhat naturally that have these parallels. Right? So that's a much more, not to use the word again, but that's a much more kind of robust kind of theory. It feels a lot better. And often with these murkier theories, all these pretty general toy models, that's what you want. You want to see that some large realm of parameter space gives rise to some pretty consistent kind of behavior. Then you can feel like you can believe it. It's not some special magical point. Okay, so the original story for this is sand parts. So granular media, very difficult, and it's everywhere. So you might think, okay, granular media, that sounds like some people. I showed you the funny thing with the ball bearings bouncing up and down the hot swans. And I mentioned this, I guess. That, of course, granular media is food, right? Rice, grains, all sorts of things that we move around. Turmeric. When you put your turmeric into another container, then it can get stuck, right? And then it's a disaster. The turmeric goes everywhere. It's fine. But right, it doesn't flow like a fluid. Sometimes it does, so that's tricky. Some circumstances it does, so we can sometimes apply Navier-Stokes equations, but generally speaking, we have to be a little more clever than that. So one great example to think about, as a bit of a test for all of these things, was this idea dropping sand. Right? So we're going to drop sand. We have a graduate student up here whose job it is to sit here and pour sand out of a little nozzle, and it lands and it starts to make a sand pump. Right? Graduate student hates you, but he's making a sand pump. And now and then you get an avalanche, right? So it will build up. If it started off as a little amount, it'll build up and you get this angle of repose, at which the sand pile can't really handle it. It can't keep getting infinitely steeper. So it's never going to get to this point. So now and then there'll be avalanches, and so some of it will slough off, and you'll keep seeing it. Right? And so then you have another graduate student down here, maybe a team, because you're feeling particularly powerful and in control, and you're paying them nothing. And then they measure how big these avalanches are. I don't know how to do that, but that's what they try to do, right? That's really tricky. So the idea was that the finding was, or the claim was, and I saw some amazing arguments about this. The claim was that the sizes of these distributions follow the power law. Okay, so that's all right. So let's figure this one out. Another odd thing is if you look at the pressure distribution underneath this, you'd think it was even. But some people would claim that it's actually, there's a dip in the middle. This is the center, right? So again, I mentioned this the other day, the force change, this idea that it's not really. So that was argued about terrifically. Physicists and engineers toe-to-toe in a memorable battle on Corsica. Not seen since the time before that, but anyway. It's a good place to have a conference. Okay, so that is, I don't know what's happened to that. But it turns out, so here's the model. Here's a model that these guys used to think about this. So imagine instead of sand, we have little blocks falling down. And instead of a graduate student, we have a computer. Outsourcing. Okay? And so this lands on this block. And if we get to 4 blocks, this is the model, then it spreads, and the blocks go into the four adjacent locations. So that's our idea of a sand pile. Right, so it's going to spread out like this. And then, so you really, if you look down from above, you see heights, right? So it'll be a height of 3, 2, 1, 0, 3, 3, 3. And the idea is if it landed on this guy, then they would still spread, which is a bit of a strange thing, right? So there'd now be 4 here, and all of them would jump out to these pieces. There'd be 4 here now, and 4 here, and they would do the same thing. So you could get these cascades. So it's nothing to do with the sand pile anymore. This is some sort of strange carpet that never has any height greater than 4. Okay, so that's a toy model. Very abstracted. And that apparently does have parallel size distributions in it. Okay. So then the game becomes, okay, was it some sort of statistical mechanical story where we can see it somehow being self-tuned to be at a critical point? Turns out that real sand piles don't exhibit this behavior as far as anyone's found. And which is disappointing. And what this is rice. So this was done in Norway by some crazy Norwegians. They went through obviously went down to the shop and 4 different types of grains. It's long grain rice. It doesn't work for short grain rice. And it's been treated in 2 plexiglass plates. And again, graduate student here, measuring the size of the avalanches. And so much contention that this apparently does produce parallel size distribution. All right. Long grain rice. But we do know that certainly with granular media you can have catastrophic kind of failures for sure. We talked about barns the other day. You can have very unexpected large amounts move around. And, think about avalanches and so on. Okay, so a bit of a funny story. So let's go back. So again, so it's this natural. So you think about these systems as being driven, right? There's something being driven. The graduate student is driving the sand pile, right? Forcing things into it. It's dissipative. There's energy being lost and smashed around. As I said, there's a self-tuning idea. You can think about something like an icing model. Somehow temperature is being self-tuned, whatever this usual external parameter is. And then, therefore, we're getting things for free, right? That would be the story. So it's Bach, Tang, and Weisenfeld. This is back in '87. A couple other papers there. And they came up with this term, which is fantastic. It's good branding, self-organized criticality. So, and they were thinking about some other pieces. So 1 over F noise is the idea that you see. Often you see frequency spectrums with power law. We're not going to touch this in this class. The power law decay in the power spectrum. Okay, so as I said, this is a problem with critical state at a very specific point. Self-tuning doesn't always make sense, and there's just an enormous amount of arguing and going on. All right, so I'll give you the Doyle and Carlson comparison. This is per Bach's great work. As I said, he passed away. He's no longer with us. But he was, I met him once. He's a very nice fellow. He was very able to rise to the occasion in meetings and in a great academic way of really going at it. But how nature works, there you go. And so that's the science of self-organized criticality. So if you can get yourself to write a book at some point that says that, that's a pretty strong statement. So maybe not. So let's look at a little comparison. So we both get parallels out of them. We have very different kind of stories. There's an optimization story here. It's a self-tuning idea, which is a little bit magical, a little bit helpful. Very important piece here, and I've said it before, so these HUD systems work over a very wide range of densities, from this critical threshold type density up to really extremely high ones. SOC has just this one density, and big comparison here is you see specialized structures in the hot one where you really saw the 4 forests, the bottom right-hand one, and the other one have not a stronger design, but it's still very good. Really clearly mapping towards the uncertainty, right? They're reminiscent of the structure of the uncertainty. And there's obvious structure. They're low entropy states. But the SOC systems produce these random generic ones. Right? They don't have an obvious optimization. This is taken from this paper that I think you should read. This is pretty great. There's a line in the paper that says, okay, so here are the properties we're going to compare SOC to HOT. We could also have another column for data, but because our model and data match up so well, we'll just... and they just say, well, these are bold claims and we'll support them. So they go. But there's a whole bunch of things in here. So, right, again, as we said, so generic kind of homogeneous, there's self-similar structures. You see these heterogeneous ones, right? They're very designed. They have some, and they're not similar. They're very different sizes, perhaps, and you get these parallels. Robust yet fragile. Density and yield, as we saw, you can get to this high densities. It's a big deal. Maximum event size can be very large in these ones, in the hot ones, which is referenced in the real ones. Well, maybe there. And this is an important piece. So the largest event size that you see, if you're really at a critical point in a normal statistical mechanical system, is fractal, right? So just when you get to that point of, say, percolation, when these points are connecting up and you can just see a large enough component that's almost macroscopic, really actually has a tendrily structure, then becomes a giant component. So other pieces in here, but let's see. All right. Yeah. So read this paper. It's just a couple of lines from it, but it is highly enjoyable. I don't think I can blow this up. They talk about what complexity, what they define as complexity. It's well laid out, and it's sort of a colloquium piece in Proceedings of National Academy of Sciences. So, very good. All right, read that one. So, cold theory. All right, so this is just a little addendum. So we had hot theory, so we have some famous physicists who come up with cold theory. So it's constrained optimization with limited deviations. So we saw that we had Lagrange multiplier type story. It's very much constrained optimization. The limited deviations are saying, well, we're going to have things exploded completely, which is what the pure hot model allows. So this is more of a design story, right? We do see these kind of big failures in the real world, so maybe the hot story is working there, or some version of it. This is more about how to design your system, not just mimicking nature or just being a little bit smarter. So simply what you do is in the design process, you weight losses, large losses more strongly. You give a bias towards saying you don't want those. And if you do that, so instead of having a parallel of sizes come out, of potential disaster sizes come out, you get a truncation of it. It's going to do two things. One is it's actually going to increase the average size of, say in this case, burnt trees, right? So it's actually going to be a little worse off on average. However, you're going to stop the chance for catastrophe, right? So it's a nice piece, quite reasonable, funny because it's cold, but this makes sense and it connects to something that's around commonly in real phenomena as well. So you talk about the truncation of these power laws, and so this is a typical kind of scenario. It does come out of statistical mechanical stories as well. There's a power law, this is probably of the size x, there's a power law with a decay with an exponent gamma, but then there's this cutoff sitting here. We think of it as a cutoff. It's an exponential, so it's being multiplied as an exponential. When you look at this, to start with, you think, well, this guy should win, right? It's an exponential, it should just destroy the thing. But if x sub c is large, let's say, in this case, 10 to the 5, then until x becomes comparable to 10 to the 5, then this number is basically 1, right? It's e to almost 0 for a long time. So it takes a long time to get out there. When it eventually gets to that, then it truncates the power. So you'll have plots like this of a power root. And so there's sort of a cutoff here, right? X sub c. So this is a log plot. Looks like a normal log, and then it gets toasted. Lots of other distributions, we'll talk about these in a second, but Weibull distributions, so there's this kind of thing, so it's x to the minus gamma. You can see you can integrate this thing actually, right? So this is e to the minus a, x to the minus gamma plus 1. This was originally invoked, I think, purely for failure distributions, right? So when gamma is 1, I'm going to say when gamma is, when gamma is, when gamma is 1 to 100. When gamma is 0, then we get, this is just a constant, and this is x to the minus 0 plus 1. So we actually get e to the minus x. So this is, if you like, a way of moving away from the exponential in a couple of different directions. Right, so So pure exponential, which have a very simple failure story. Then there are these ones that have a power, so it's sort of a memory thing going on here. All right, those things can happen. We'll come to this later on. Network robustness, we've talked about things collapsing. There's some hot story in here as well, but there are a couple of pieces when we get into complex networks, which will start next week. Huge, huge, huge topic, gigantic topic. And there are a couple of classic pieces in here. This is Albert and this is Barabazi as well, so this is thinking about what kind of, it's different for hard. So which networks are vulnerable, which ones aren't, based on random or directed kind of attacks. You know, kind of, it's an old story, you can generalize that in all sorts of ways. And then after we go through networks, we'll get to contagion, spreading, so we'll look at biological contagion. And these are just very fundamental things, right? Diffusion, if you like, is the most basic kind of spreading there is. It's everywhere. Spreading is just an enormous part of systems in general. Right? Ideas and stories for people, diseases as well, behaviors, but you think of biology, spreading, copying of genes and so on, it goes all the way through. Right. So, but we'll think about things spreading on networks, that's a big deal. And so there are some really interesting stories, again, here about robust yet fragile kind of systems. Things all look good, suddenly they can explode into flames. All right. Okay, so there we go. So that's hot. We'll work on some of that good stuff. And I wanted to talk about language. Nope. Oh yeah, so it's just a little bit about this. This is going to be about irregular verbs. You see that these guys made the front cover here. And there's a lot more that can be done and will be done. You know, we have Google Books, which is a tricky thing to do with, but we have access to a really interesting phenomenon, which is a fantastically important thing, which is human language. Very, very rich. So this is from 2007 now. So looking at how language evolves, right? So and I didn't read this out the other day, but I had this rejoinder at the end of that I was going to point out at the end of Mandelbrot's article. So Mandelbrot's article about optimization has a couple of people saying some things about his article, just as built into the structure of that book, and then he has a reply. But one of the comments is Mandelbrot is complaining about Mandelbrot having evolution, essentially talking about optimization in language. And there's some statement like it's axiomatic that, to paraphrase, it's axiomatic that language has no direction of evolution. Just doesn't. This is 1953. Well, so there are definitely some patterns, and we've certainly changed as we've moved, say in English, as we've gone from Old English through to Modern English. One of the things we've done is move more to the importance of context, which is a very interesting phenomenon, right? So it used to be, if you have a frog jumping over a pond onto a snake or something, then when you have the word jump, it would have something. This is not really true, I'm just mixing it, but the jump would have something about a frog in it and a pond and a snake. They'd be hanging on them, right? So you have all this structure in the conjugations, which would tell you gender, and it's still in languages for sure. But it's been dropped out of English, so you have to listen to the words around things. You can't tell quite as much. So it's an efficiency story. Right? We've realized that okay, you can communicate with less structure, and we're fine. So we're looking at this is looking at verbs. It's just looking at verbs, and it's irregular verbs. There aren't many irregular verbs. There are about 150 roughly left in English, and it's all mainly about their conjugation of the past tense. Right. So instead of saying I teached, right, I taught. And it's funny because we think it's horrible when people mess with those sort of things. Right? Kids do it all the time. They try to use the ED ending because that's this huge rule that everyone's presenting them with over and over. And then when they say I be good, then we think it's just it hurts to hear it. But it's just purely programming for us. So that's this investigation. I just want to present this. piece, and lots of other aspects of language. The future tense is all standardized, right? So I will go, I will teach, it's all I will. There's no structure in there. And there are a couple of funny other pieces in there with, of course, there's also present tense, I am, you are, and so on. Right? Structures like that. There are two, there's so I say, you say, he says, she says. So the oddness in there is not the spelling, which is actually consistent with regular kind of spelling, but they say, we say. But you don't say says, like he says. Right? So that's a pronunciation thing. So there's that, and so they're the very common ones. The other one is what's the other one? Do, right? I do, you do, he, she does, which is instead of do's, right? All right. So you don't notice these things, right? We don't notice language because it's like water to fish or air or something. We just don't. We can think about it, but a lot of the time we don't notice it. Who knows what I've been saying? All right. So a couple of interesting parts. So this is the number of irregular verbs as a function of their frequency of usage for example text from corpora, from Old English, Middle English, and Modern English. So you see that they all match up for very common verbs. So to be and to have are they're the most common ones. And they haven't changed. Right? That's what this is saying. But there's been a loss of irregular verbs in these other categories out here. And there aren't so many irregular verbs that are very rare. But the biggest losses are here in these more common ones. And so when we introduce a new verb, it's hard to make a new verb, and this would be an impressive achievement. First of all, introducing a new word, that's obvious. But also to make it irregular in conjugation if it's a verb, right? I Google, she Googles, he Googles, right? We just don't do it. So, we like these rules. So, so this is again looking at, so now you want to look at this. Okay, so there are less words, more or less words at different frequency ranges. They bend them in a particular way. So you can look at the rate at which they have disappeared, and there's this nice little scaling wall that pops out. There's not a lot of data in here, but it's a pretty interesting thing. It's not explained actually, so if you can figure this out, and if it is true, then it's a big deal. So there's two things: it has to be true, and you have a story for it. So it's about -1/2, right? So the rate at which verbs are regularizing depends on their frequency to the power of -1/2. So the more common a word is, the lower the rate is. It's just hard, right? To be and to have, it's hard to turn them into I be, you be, she be. But it's not going to that really hurts because we say it so much. That's the story. Right? So the more resilient it is to change. But this is a pretty remarkably clean looking thing, if it's indeed all true. So they have a nice table here, you can look at this perhaps later on. These are in black are words that have stayed, and red are words that have changed. And so you need to think about your knowledge of these guys. So for instance, fly is sitting here and flew. And some of these, of course, are gone. Right? So smoke, I don't know what the past tense of smoked. Smoke to cover driver. I don't know what it was and it was before him. Smuck. So smite is in there, that's a good one. You smoke. You smoke him. Great words. I mean, it's a sort of a tragedy, right, to lose it. So there's understood and through, taught, won. But one, and you can look at which words are on the cusp. So wed at the time of this was kind of on the cusp, right? So two people were wed yesterday versus you were wedded to an idea. So in those different usages, the ed is sneaking out and taking on some structure. Okay, so I guess, yeah, I don't know what reach was, but now it's reached. But we're fine. Bait was baked. So Anyway, very nice stuff. And you can see the rates. So this is, again, just another version of it that's showing you the words. Where did I say is the next one to go? And if you look at this, right, so this is the, again, this is this plot from the other side. So this is trying to put it now on the time axis. This is, I'm sorry, the plot that we showed at the start that was all collapsed. The idea is now to go back in time further, and the claim, I don't know this one. The claim is that if you go back in time further, this will start to open up more and more and more, and you'll in fact kind of get a nice SIF distribution, right? So, sort of in a sense, this kind of theoretical, possibly never really existed story that if you go back in time and to some proto-language, then all of the verbs are irregular. And they have, it's opening up in a nice way. And you kind of estimate the time that it would take. And, oh, I don't want to put this in. Okay, so it's not on this slide. But they have estimates for the half-life of the most common ones, right? To have, maybe I haven't. So, but I think it's like 40,000 years, something like that, before they regularized, which Orwell would enjoy. Okay, so that's very enjoyable. There's another piece here that I'll come to later on, but it's basically, it's about the number of meanings per word, which has an interesting behavior. Yeah, okay, so here it wasn't. So half-life is proportional to the word frequency to a half, right? So this is going the other way to the regularization rate. So the very common ones to be to have are going to hold on for the longest if we ever let them change. I mean, it's a charming aspect of particularly English is the sort of insanity that's built into it, right? And I think that's why, to my mind, the English are some of the fun. I mean, they're not very good at anything else, especially sport, but except for inventing sport and being beaten by other teams, which is enjoyable for colonies of the world. Losing empires, they're good at that. But it's the it's language. You know, you have Monty Python, you have all these crazy things, and I think it's kind of my hypothesis is because the language is absurd. Okay. All right. That's a little sort of a diversion, but you know, finding these structures in unusual places. We'll do that one. How am I doing? Okay, so we're going to start on this one. I'll finish this next Tuesday. Just a reminder, we have the Jake Williams factor will be here on Thursday to talk about his extension of Simon's model and the whole word counting thing to phrases, which is a huge deal. Huge deal. All right, so we're going to talk about some patterns here. This confusability of all of these heavy tail distributions. So we'll just start with, I'm going to talk about lognormals, and then a couple of other, so talk about them for a little bit, what they are. I'll give you a very simple mechanism for how these arise. We'll tweak that mechanism in two different ways, and we'll get very different distributions as a result. So it's just to kind of partly give you a warning about where these things can go. But these are very common ones as well, so it's important to look at them. All right, so these are the heavy tail distributions. We'll look at this one in depth. It's the log normal. So you can see instead of an x up here, this is of course the structure of the normal distribution. So log x. There's also an x floating around here. Right, that's the tweak. We'll explain that. I talked about Weibull distributions just before. Stretched exponentials, another thing that you see, gamma distributions, lots of other possible guys that have some kind of parallel structure. All right, so why does this? I mean, sitting here with an exponential, surely that should crush things, but as I sort of alluded to before, it's an exponential, there's a log up here, so it's going to be a little slow, and there is a 1 over x sitting up the front. So this guy, essentially, we'll see, can masquerade as a 1 over x kind of law for, depending on sigma and mu in here. All right. Said these words. So log x itself is distributed according to a normal distribution. Right, the log is. You see it in lots of different fields, so economics and biology, in particular, where you're talking about. Sometimes, of course, you have negative amounts of money, but you're thinking about growth. So there are some, you can go through and compute all these things. It's not the same. Okay, this is the format I put up before. The actual, you're talking about the average of the underlying normal distribution, or the mean and the standard deviation. Those things are mu and sigma. But if you go through and really compute the mean for this different, this log normal, then you get this kind of structure. Right? So it's E mu plus a half sigma squared, so it's mixing the mean and the standard deviation get involved in lots of these things. But the standard deviation is more complicated here. There's, you can actually figure out what the mode is and the median and so on. So that's fine. But they are different pieces. Often we talk about the underlying normal distribution, but it's good to know these things. So very different to power laws, right? So it's this piece that all the moments are finite. So we're not going to get these, this issue we have with the random walker coming back, but on average taking an infinite amount of time. The average for these guys is always finite. It can be large, but still finite, even theoretically. All right, so how do we get there? So this is, so imagine how we have this y is distributed purely as a normal distribution, standard thing. Then we'll put y as log x in here. Okay? So we're going to transform to log x. So we've done this variable transformation a bunch of times. You have to replace the dy. First of all, we put the y as log x, so that's just done. The dy piece, that's here, so dy dx, if we've got this transformation y equals log x, so dy dx is simply 1 over x, so dy is dx over x. So that chunk goes into here, and that's where we get that 1 over x appearing from the Jacobi. All right, good, so we're off. Now it's x's. Here's a comparison. Log normal is in blue, the dashed line. A power law with gamma equals 1, right, which we know is a very extreme case, but it's almost not normalizable. You can see that these guys are pretty similar. Over, this is many orders of magnitude. In fact, they're really matching very well. 4 orders of magnitude. Deviation isn't super strong. You know, little flax, you might just draw a straight line through the whole thing. But the big deal here is that this is a log normal that had a high, it comes from a distribution that has a high standard deviation. So it's got some weight. All right, that's a bad thing. So what's happening, so we can just go through this. So if we take log of this distribution, so we take log of the whole thing here, because we, on this slide here, we're plotting log of px. So log of px is a function of log of x, so let's look at what those things are, how they're related to each other. So we take log of p of x, log of this whole business, all these things are going to blow apart. So there'll be a minus log x for that 1 over x. This is just a constant here. Maybe the sigma got lost, but this whole piece is sitting here. And this is an exponential, so it's log of an exponential. We just get minus log x minus mu. This whole chunk comes down, squared with 2 sigmas. Good. So we're going to fiddle around with this a little bit. You see, this is just a quadratic in log of x. So if we expand that and collect terms, then we get this blob times log of x squared. We get a blob times log of x, and then we get a couple of constants on the end. So log of p of x. This is not no corrections here. In log space, and of course we need to change it into base 10 to be really good people, but we're just getting a structure. It's just going to be a scale factor. Well, a little bit, yeah. So this is a quadratic. So this piece eventually starts to dominate, and it moves away from being a linear relationship, right? So if it's just this, then it is a power law. This is the piece that takes it away. So if this piece, okay, there's a couple pieces here. So if this is relatively small, compared to this, log grows very slowly, and mu of a sigma squared is small itself, then this looks like minus 1 log x. Right? So if this disappears relatively and this disappears, then it looks like we have minus log x. So it looks like a gamma of minus 1. So that's a nasty, sneaky thing that could happen to you. And the reason we're talking about lognormals is because they appear so often. So there's just some extra stuff here. This is roughly true when you know, we're trying to figure out when the lognormal will start to move away from looking like a power law. Just skip these slides. That's fine. That's just some extra stuff. Okay, so where do we get these things from? So the simplest mechanism, natural kind of mechanism, it's not a competitive one, which we said was true of the Simon model, the competitive models, right? You have groups competing for new members. This is just imagining, this is again like the random walk model where we're looking at an ensemble of random walks. Right? We're starting off all these random walkers, and then we're adding up all of the final behavior or the behavior at time t. That's the same story here. So everyone starts at the same time, we let them grow, and then we look at how our distribution is evolving. So it's a random growth model. That's what it is. That gives you, it's the simplest thing that gives you a log model. So this should immediately make sense if you think about the central limit theorem. Normal distributions coming from additive things, right? But we're in log space. So R is a factor that's greater than 0. You can have shrinkage, right? So R is less than 1. Seinfeld. Okay. Growth is by addition in log space. Okay, if you take log of this equation, we get log of this quantity log of x is growing by some random increment, which, because now we're in log space, that could be a negative number. So that gives us that the log of xn is normally distributed, maybe with a growing mean or shrinking mean, and therefore the x itself is distributed log normally. Okay, so it's an incredibly simple model. I mean, that's the simplest thing you can imagine. So this is the money you have in the bank this year, this is next year, this is some horrible number, it's distributed. It's at least it's greater than 0, but you know, it could be rather small, right? So, so this has been around for a while, and there's lots of arguments here. So this, you can go back to 31, you have Girard uses this to this simple model to explain the distributions of firm sizes. This is a bit funny though, because we have Rob Axtell, who we have a nice connection with. He gave a talk at our first TEDx talk. Members of our group have worked with him. So he has a parallel that fits the data very well, but it's gamma equals 2, so I'm not sure what was going on with Girard, but it's gamma equals 2, not 1. So it's not really a log normal story. So Axtell, this is a science paper, it's well read. It's one of those papers that's about 2 pages long, but it has 100 pages of supplementary information. And many orders of magnitude. So here we have 6 orders of magnitude. 2, 3, 4, 5. Yeah, and these are jumping. It's 10 to the minus 1, 10 to the minus 4, 10 to the minus 7. So the bigger range here, 12 orders of magnitude here. So this is the firm size in terms of employees, just number of people. So this is very well fit by a 2. So this is a pretty spectacular plot, this one. So he uses a different model because it's not getting 1. So, all right, so this is one piece that seems to fit, and we'll use it, we'll keep using it, which is that this growth rate R, which is random from year to year, if you like, or from month to month, depending on how you're doing it, that appears to be independent of firm size. So that was an important assumption about that original very, very, very simple model. It doesn't matter what size you are now, your growth rate is drawn from some distribution, which is greater than 0. So we can keep that. So here's an argument for why you might get these kind of exponents. Should be gamma is equal to 2. So we're going to do something a bit different. There will be a somewhat, not competitive, but there's an interactive piece now, so that these entities have some connection to each other in a bit of a funny way. So you have n entities. They have these sizes, x and y, and they are growing in the same way, right? Same kind of story. So they're all growing. This its distribution is nothing bad, simply that it has to be greater than 0. So it's all the same except one extra piece. They just change one thing. So this is a bit theoretical, but it's very useful to see what tweaking things just in a tiny way will do. So the size of the firm, one of these firms, at the next time step is going to be the maximum of what we had before. This is the same equation of, right, so we randomly draw this out. Some fraction, some amount of the previous size. Or it will be, there's a minimum in a sense here. So this is some constant, which is fixed, times the average sizes of all the firms now. So it's a little quirky, but it's a way of creating now a boundary that's not 0. So so in the log normal story, where we just have this piece, you can get it arbitrarily close to 0, the firm size. This is to say that there's some minimum. And that changes things completely. All right, there's a problem set, a question for this one. You find again that you get a parallel distribution out, and you get a relationship that connects the exponent gamma to this C, which is fixed, the number of firms. Some fun, right? And if you mess around with that a little bit and you say, well, this constant is whatever it is, but it's much smaller than the number of firms, you can play around with that a little bit, and you can get gamma is 1 plus 1 over 1 minus C. So if this C is a small number, then we get this, so it depends on what that C is, then you get gamma as approximately 2. The idea of C being very small means you've changed, you can be incredibly small, and you've changed the problem in the most minimal way before, from before. Right? So we had stop it. Wow. Yes. Someone needs a new battery. Okay, so this C could be incredibly small, right? And that's enough for all of this theory to work out. So that's odd. Just tweaking in the tiniest possible way. And suddenly we have a very different thing. So now we have a gamma of approximately 2, so it's not a minus 1, 1, and it's not a log normal. So that's a little scary, right? The mechanism's changed a little bit. It hasn't changed the exponent by a little bit or made a log normal with an extra tweak on it. It's a fundamentally different distribution with quite a different exponent. And, okay, so I'll tell you this one as well. And that will be where I want to get to. So imagine now that we allow this, we go back to what we had. So we have this random growth model, and firms or entities can be arbitrarily small. But we start them at different times. We just simply start them at different times, which is also a very reasonable feature of the real world, right? So firms come into existence at different times, whatever it is we're talking about. Obviously not the same. So this turns out to have very different odd consequences. So we're going to allow the number of updates to have occurred for each side, for each entity, to vary, right? So this, and here's a ridiculously simple one. Let's imagine that the ages of these entities is distributed exponentially. So a very benign distribution. And we're going to allow, as I said, to have no bottom limit. We're going to have each xi is going to follow a log normal. Right, so if you take one of them, or you take all of them that start at a particular time, and there's a whole ensemble of them, then we'll get the log normal story back again. But now we're putting in the same boat, we're putting ones of different ages. And the way to treat that is, well, we know we get a log normal, that's the piece in red, but the probability that x will be of a particular size, well, we're going to sample from a log normal that's been running for t time steps, and we have to sample from the ages, right? Because we want to pick a random entity out. So we have to pick it out and we say, okay, with probably this, according to this distribution, this is how old it is, and then we have this probability of how big it is. So we know it's growing log normal. So that, okay. Do you think maybe you do this interval and you kind of get some sort of smooth log normal out? that could possibly make sense. This is some sort of average. But don't worry about it. So now we're right. That's what we're doing. We're averaging different log normals. This will be just a useful convenience. We're going to put mu as log n in here, so this can be collapsed to log x over n. You can work on this. It's an interesting problem. And then you get to this. So now we get something else completely different. So now we get a 1 over x at the front. And then there's an exponential here that has a square of log x in it with a square root of it. So we have to be a little careful about that. So we'll treat that on the next slide. But if it was just e to the log x, that's x, right? Or e to the log x with some power, then that should just pops back out. So this is very simple. So if we have that, that's the previous slide. It depends on the sign of log x over n. So it's log of x over n. And that depends whether x over n is greater than 1 or smaller than 1. Right, we'll get a sign out. So we have to cope with that. So if it's less than 1, then we replace, this will be a negative quantity, and we put a negative sign. We take the square root away and put a negative sign there. So then we get a plus root 2 lambda. If it's positive, then we just leave this as negative plus the whole thing. We get square root of 2 lambda. Just this pops out, and that'll be minus root 2 lambda. So we get a break in scaling. We get 2 power laws, and we get a break in scaling. So it's not a log normal anymore. What's happened is it's taken something that kind of looked like an x minus 1, as we said for log normals, but it's tweaked it around a particular breakpoint. So it's a break in scaling. We've talked about these things. It's sometimes called a double Pareto distribution. There's one from Schlesinger. Came across this a while back. And this was actually used by Huberman and Lara Adamic. Bernardo Huberman, who's at HP Labs. Lara is she's at Michigan. So this is for the number of pages per website that people visit, I think, clicking. And they, of course, go somewhere else. Show that you got this sort of thing. All right, so here's the little nutshell. So log normals can look like a particular kind of power law. We can get these, so we saw these log normals come from a very simple kind of growth mechanism. It's non-competitive, multiplicative growth. If you put a little minimum size in there, suddenly we get a power law tail. Crazy. No minimum size and distribution of lifetimes, we get this double Pareto. So it's another kind of power law. Be very, very careful. All right, so there's sort of a zoo of these things. We've looked at some of the animals in the zoo, the big ones that everyone goes to see all the time. But there are some sneaky other ones that you need to visit as well. All right. So Jake Williams will be here on Thursday. And yes. So next week is complex networks. Very good. Very good. Very exciting. Huge.